Hi everybody. Last time we spoke about how we can figure out some initial unknown quantum state through a series of measurements, in particular by performing a handful of different experiments many times each over a large number of identical systems. This time we're kind of going to go the other way around. We're going to start with the system that we know, and we're going to learn a little bit more about how we can represent our expectations of what many measurements of such a state would yield. And one very common way, the most common way to represent this in quantum mechanics, is through what we call an expectation value. An expectation value is really a fancy word for average. You kind of actually already know what an expectation value is. This is related to a terminology from statistics called expected values. It really is the same thing as that as well. But again, what we really mean by this is an average. And to demonstrate that, let's do an example, just from normal everyday life. Imagine that there's a zoo. And in this zoo, there's a herd of elephants. And in this herd of elephants, some of the elephants are babies, some of the elephants are adolescents, and some of the elephants are adults. As you can see here, we have 4 baby elephants, 3 adolescent elephants, one of them is a little out of control, and we have 5 adult elephants. And for the sake of this, let's say that the baby elephants each have masses of 300 kilograms, the adolescents are 2,000 kilograms, and the adults are 5,000 kilograms. Imagine that you're just minding your own business, tending the zoo, and a little girl comes up completely enamored by elephants, and rightly so, of course. And she asks you, how big are the elephants at this zoo? How do you answer her? There are a lot of different ways that we could choose to answer her. You could list out every single elephant at the zoo and explain to her how massive each one of those is. Or you could say, well, there are 4 babies that are 300 kilograms and 3 adolescents that are 2,000 kilograms and 5 adults that are 5,000 kilograms. Or you could simplify a little bit and say, oh, the babies at this zoo are between 300 kilograms and 5,000 kilograms. A really common way of answering questions like this is through averages. We would say, well, the average elephant at this zoo has a mass of blank. Well, how do we calculate this? There are different kinds of averages, so we have to specify what kind of average we mean. The 3 most common kinds of averages that you'll see are medians, modes, and means. So the median would be, if we have a total of 12 elephants, so the 6.5th elephant, what is its mass? Well, the 6.5th elephant is an adolescent. And the adolescents have 2,000 kilograms. So the median mass of the elephants in the zoo is 2,000 kilograms. The mode is the most common number. And so we have more adults than any other individual kind of elephant. And so the mode average, if you will, is 5,000 kilograms, which is really to say that 5,000 kilograms is the most common mass among the elephants at the zoo. The third common average that we use, in fact, the most common, is the arithmetic mean, or we're just going to call it the mean. The mean is a little bit more complicated to calculate, certainly not particularly challenging, but what we do is we take the number of times each instance appears, we multiply that number by the value of that instance. We do that for each of the different values, and we divide by the total number of things. So in this case, we have 4 babies times 300 kilograms. We add to that 3 adolescents times 2,000 kilograms. We add to that 5 adults times 5,000 kilograms. And then we divide that by the total number of elephants, which is 12. 4 babies, 3 adults, and 4 babies, 3 adolescents, and 5 adults. That gives us 2,683 kilograms per elephant on average, according to the mean. Now, maybe that's not the best answer to give the little girl. Maybe that's not going to really mean much to her. Maybe you want to tell her most of our elephants are 5,000 kilograms. That's not entirely true. Most of your elephants are babies or adolescents. Or maybe you want to give her a range or something else. But either way, the point is, when we're talking about a large number of things, there are different ways of quantifying it. Obviously, the most complete way of quantifying it is providing all of the information. There are 4 babies at 300 kilograms, 3 adults at 2,000 kilograms, and 5 adults at 5,000 kilograms. But sometimes that's a lot, and it's not all needed. Sometimes we just want the big picture, and that's what we use averages for. Now, in quantum mechanics, because our experiments, in order to be meaningful, have to be repeated many, many times, it means we are inevitably dealing with large numbers of events. If we aren't dealing with large numbers of events, we have actually very poor information. So we're almost always going to be dealing with these large numbers of events. I can't think of any scenarios where we ever really care about the median. There are certainly times we care about the mode. In the context of quantum mechanics, we would call the mode the most probable value. And in quantum mechanics, we give the mean a different name. We call the mean the expectation value. Now, you might notice that the expectation value is a little bit of a misnomer, right? For example, if I were to look in my zoo and I were to say, okay, I'm going to pick a random elephant out of the 12. What do I expect the result to be? Well, the expectation value that we calculated, the mean, was 2,683 kilograms. What is the chance that one of the elephants that you pick out of this group will have a mass of 2,683 kilograms? It's 0. None of them have that mass. So the expectation value, the term makes it sound like this is the value you expect to get if you perform the measurement. But that's not necessarily true. And in fact, frequently, the expectation value is a value that you can't get, that there is no object or no instance of event or whatever with that value, such as in this case with the elephants. I don't know why we call this the expectation value. I don't know who came up with this terminology, but it is nonetheless the name that we give it, but it really simply means the arithmetic mean. It is incredibly important in quantum mechanics because the expectation value or mean of a measurement has a really important physical significance that we'll talk about in a bit. First of all, let's talk about some notation. So if we're talking about the mass, the expectation value of the mass is written like this, with these 2 pointy brackets on either side of our variable, or of our measurement, I should say. What we're going to do now is we're going to use the elephant example to work out a general expression for the expectation value. And I'm going to use the context of probability but because that's what quantum mechanics is all about. So if I want to find the expectation value of some variable x, if you look at what we have over here, this first term is 4 babies out of 12 elephants. Well, 4 out of 12 is like a probability. And 300 kilograms is the value of the variable. And so this first term is the probability of there being a baby elephant times the value of mass for the baby elephant. And likewise for the second term, we have the probability of finding an adolescent elephant, 3/12, times the value of mass for the adolescent elephant, and so on for the adult. So the equation for the expectation value is the sum of the value of x times the probability of getting x, added up for all possible values of x. This is explicitly for discrete situations where there are only a finite number of possible measurements. If there are an infinite number of measurements, we have to deal with integrals, and luckily with quantum spin, there are only ever finite possibilities. So let's actually talk about this in the context of spin. So let's consider a simple quantum mechanical state, psi is equal to z plus. If I want to know the expectation value of a measurement of spin in the z direction, I add up the value, I add up the value of spin that I can get times the probability that I will get that spin for all possible values. Well, we know that if I measure spin in the z direction, there are only 2 values I can get. I can get h bar over 2, and I multiply that times the probability that I get h bar over 2. And I could also get negative h bar over 2 spin, and I multiply that times the probability that I would get negative h bar over 2. Well, in this particular state, we can rewrite our state z plus to be 1 z plus 0 z minus. And I'm not going to go through the calculation, but we can easily show at this point that the probability of getting negative h bar over 2 is 0 because the probability amplitude of getting negative h bar over 2 is 0. And so and likewise, we know that the probability of measuring positive h bar over 2 for this particular state is 1. And so in this case, the expectation value is simply h bar over 2. Now, a measurement of spin in the z direction of a state that is simply z plus is basically as trivial as we can get every single time. This is a state of definite spin, which means every time you measure spin in the z direction, you will always get the same thing. So the average, or the mean, or the expectation value in this case is no different from the median or the mode because you will only ever get one value. So the most common value is also the middle value, and it's also the arithmetic mean of all the possible values. So let's ask a slightly different question. I want to know this time, what is the expectation value of a measurement of spin in the x direction of our state z plus? Well, to do this, the easiest thing to do is to rewrite our z plus state in terms of the x basis, although there are other ways of doing it, and we'll talk about some of them in a bit. But once again, I know that there are only two possible values of a measurement of spin in the x direction. Once again, you'll only ever find either positive or negative h bar over 2. And so we're going to multiply those by the corresponding probabilities of getting those values of spin for this particular state. In this case, a measurement of plus h bar over 2 in the x direction and minus h bar over 2 have probability amplitudes of 1 over square root of 2. So they have probabilities of the magnitude of that squared, which gives us 1/2. And so we multiply plus h bar over 2 by 1/2, and we multiply minus h bar over 2 by 1/2, and we get a result of 0. This is a more interesting result than before, because every time I measure a spin in the x direction, I get either h bar over 2 or minus h bar over 2. I will never get 0 spin. It's not one of the options. Every time I measure the spin of an electron, I always get h bar over 2 in some direction, never 0. So the expectation value here, kind of like in the example with the elephants, corresponds to a value that you will never actually get in your measurement, which is, again, why the term expectation value is a little bit of a misnomer. I do not ever expect to measure a value of 0. The expectation value is, what does the average value trend towards over a series of a large number of measurements? And after performing the measurement in the x direction many, many, many times, I expect to get positive h bar over 2 just as often as negative h bar over 2, and so the average result of my measurement will be 0. Now, so far we've been calculating this by inspection. I'm looking at the probability amplitudes, and I'm calculating the probabilities, and I'm plugging them into this expression. And that's all well and good, but we started with a really simple state, a state that was, as simple as can be in the z basis, and pretty straightforward in the x basis as well, and it happens to be a state that we immediately know how to convert it to the x basis without a lot of effort. But if I give you a more complicated state, for example, like the one from the previous homework assignment, and I ask what's the expectation value in the x plus direction, in the x direction, or in the y direction, it becomes a little bit messier, and I have to do a lot of conversion before I can actually start to do the work. There's a cleaner way of going about this, though, that makes use of our measurement operators. To see it, though, we have to do a bit of work. So we're going to actually start by talking about the expectation value in the z direction for an arbitrary unknown state psi. And we're going to start by writing down the definition of the expectation value, like we did before. But we also actually know how to compute the various probabilities of our state psi being measured as plus h bar over 2 or minus h bar over 2. So we can express the probabilities as those amplitudes squared. And remember, a magnitude squared means I'm multiplying a number times its own complex conjugate. Well, this inner product here is a number, so I'm multiplying this inner product, z plus with psi, times its own complex conjugate. I'm going to use an identity here that I showed you at the a while ago. We were still in school at this point. That the complex conjugate of an inner product is simply the reverse. So I simply switch the two. If you don't remember why, you can always look back in your notes. I'm not going to go through the proof right now, but if you represent, if you want to figure it out for yourself, if you represent two vectors as just like row and column vectors, you can show it with not a ton of work that this is in fact the case. Now, I want to remind you that this psi is a row vector. This z plus, this ket, is a column vector. This is a row vector. This is a column vector. This is a row vector, column vector, row vector, column vector. Now, matrix multiplication isn't commutative, which means I always have to multiply from the left. I have to multiply psi times the thing on the left. I can't multiply z plus times this psi. But I can multiply this z plus times this psi first, and then I can multiply this onto the result of that, and so on, as long as I'm always going from the left. But I can calculate from the left over here, and then I can calculate from the left over here onto that result. That applies between these two vectors, z plus, the ket and the bra here. Now, the first one is a ket. It's a column vector. It's the column vector 1, 0. The second one is the row vector 1, 0. I don't have to worry about complex conjugates of these because they have real values. So the complex conjugate is just itself. Now, this is a little bit different from the matrix multiplication we've been doing. It's the same process, but this time, remember, when you do matrix multiplication, you get the number of rows of the first matrix and the number of columns of the second matrix. So this is a little bit unconventional because I have 2 rows, 2 columns. So this vector times this vector in this order gives me a 2 by 2 matrix. And it gives me a 2 by 2 matrix where the first row is 1 times 1. The first row and first column. The next one is 1 times 0. And the next one is 0 times 1. And the next one is 0 times 0. I can do the same thing for this z minus, where the z minus ket is 0, 1, and the z minus bra vector is 0, 1. Again, I don't have to worry about the complex conjugates for these because they only have real values in them. And this gives us the matrix, if you work it out, 0, 0, 0, 1. Now I'm going to rewrite the previous line, but instead of writing the z plus and z minus vectors like this, I'm going to replace these products with their corresponding matrices that we just calculated. Now I can make use of the distributive property of matrix multiplication to combine these two terms so that I'm sandwiching a sum of these two matrices between my bra and my ket vector of my unknown state psi, or arbitrary state psi, I should say. Now I'm going to carry out this subtraction between these two matrices, and I'm also going to bring this h bar over 2 inside here. H bar over 2 is just a number, so I can multiply it wherever and whenever I want. It's an overall factor. This should look familiar. H bar over 2 times this matrix is equal to the SZ operator that we found in the previous homework assignment. So I can write the expectation value of a measurement to spin in the z direction on the state psi as the measurement operator SZ sandwiched between the bra and the ket vectors of the state that we're measuring. Now you can see why we use this to symbolize the expectation value, because the expectation value is basically inserting the operator corresponding to the measurement that we're looking at in between sort of the bracket of the state that we're measuring with itself. What we've really shown here is that if you multiply the eigenvalue of the SE operator corresponding to the Z plus state times this weird kind of product of Z plus with itself but backwards, and you add to that the eigenvalue of the SE operator corresponding to the SE minus state times the similar product for SE minus, you actually get the operator SZ. This process actually works for any operator, any finite dimensional operator. If you know the eigenvectors and the corresponding eigenvalues, you can always construct the operator by simply multiplying the eigenvalue times this funny product of the eigenvectors with themselves according to this fashion. So if I want to find the expectation value of the Sx operator acting on my arbitrary state psi, I can write it out the same way. I can apply the same substitutions as before, and I end up with the exact same expression, except instead of having my Z plus states here sort of sandwiched in between, I have my X plus states, and I can write this the same way as before, as the Sx operator sandwiched in between the state that we're measuring. This, of course, works for Sy as well, and in fact, it works for a spin measurement in any direction you could possibly choose. So let's do an example. Let's use this method to actually compute the expectation value of a state. I've made sure to construct the state so it's normalized, so it has a total probability of 1 of being found in either Z plus or Z minus. The first thing we're going to do is remember that I can represent this as a column vector. Since Z plus is the vector 1, 0 and Z minus is the vector 0, 1, I can rewrite this state as follows. Now I'm also going to need the bra version of psi, and the bra version of psi is the transpose, which means I take my column and I make it a row, of the complex conjugate, which means I flip the sign of every I that showed up in my vector or my matrix. There's only one of those, so I only have to flip one sign. So I have my bra vector over here, and I have my ket vector over here. Remember, bras point to the left, ket point to the right. Now what I want to do is let's find, first of all, the expectation value of a measurement of spin in the z direction for this state. Well, what I do is I sandwich my state, my operator as z between my bra and kets of my state that I'm measuring. I can write down my bra vector of psi from above. I can multiply it by the spin z operator, which I know the matrix form of from our previous homework. And I can then multiply that by the ket of psi from above. And at this point, I'm done with physics. I'm doing math. That's the nice thing about calculating expectation values this way. Yes, I could say, okay, well, this is the probability amplitude. I can take the magnitude squared of this, and that tells me the probability that I get plus h bar over 2. So I can add that to minus h bar over 2 times the magnitude squared of minus 1 over square root of 2, and I can get my expectation value. Or I can just plug and chug. I can convert this into matrix form, and I can just do the matrix multiplication. In this particular case, there's no big advantage to doing it this way. In fact, it might even take me longer to do it this way than to just do it in terms of the probability amplitudes. But as we'll see, in other cases, this method is going to be a lot faster, certainly more straightforward. But if we multiply this out piece by piece, we slowly, eventually get to our answer. Note that I chose to multiply the middle matrix times the right matrix first, and then I multiplied the left matrix times the result. I could have instead multiplied this onto the middle matrix and then multiplied that result onto the right matrix. It doesn't really matter which way you do it. Note, by the way, in this term over here, what I've basically done is I'm multiplying h bar over 2 times the probability amplitude here times its own complex conjugate, which is the probability of getting h bar over 2. And then over here, I have the amplitude minus 1 over square root of 2 times its own complex conjugate, which is also minus 1 over square root of 2. But I'm missing a minus sign in here because I'm multiplying negative 1 over square root of 2 times negative 1 over square root of 2 by negative h bar over 2. And so one of those signs has already canceled out. So I get the same result whether I do it sort of by explicitly analyzing the probability amplitudes or by going through this computation. So let's do an example where it's easier to do it in terms of these matrices. The simplest example of that is to look at the expectation value of spin in the x or in the y direction. Let's pick the y direction. Note that if I want to do this the old-fashioned way, I either have to convert z plus and z minus into y plus and y minus, and then I can read off their probability amplitudes, or I have to compute like y plus psi, and I have to express y plus in terms of z plus and z minus, and I have to go through all that. And that ends up being a whole bunch of work. Now, this method with matrices is also going to take some doing, but I think it's a little bit simpler. So once again, I can write down my bra vector from above, and I know my sy operator from the previous assignment, or 2 assignments ago, and I know the ket vector from above as well. Again, we've finished doing physics. Now we're just multiplying 3 matrices by each other. So again, we can work this out step by step. It's a little bit more involved, but really, this isn't... Notice that doing this for sy is not really any harder than doing it for sz was. It's a little bit more complicated because we've got i's. But other than that, it's the same thing. Now I got 0 again for the expectation value of spin in the y direction. That's not always necessarily going to happen, right? Just because the expectation value in the z direction is 0 doesn't mean it will be 0 in the y or in the x direction. In fact, if we compute this in the x direction, I believe we would get something other than 0. But this is the process of how to go about computing expectation values. And again, this method makes it straightforward. It makes it the same thing every time. It doesn't matter whether you want sx, xz, or sy. It doesn't matter what basis you have your vectors in, or it doesn't, right, whether you know it as z plus or z minus. You just calculate it. And whether I do it in sz, sy, or sx, it's about the same amount of work either way. Whereas if I want to do it this way, I have to deal with the stuff that you had to do in the previous homework assignment, which leads to a whole bunch of algebra. The last thing I want to go over in this video is why. Why do I care about the arithmetic mean or the expectation value in quantum mechanics so much? Right, in the end, it is an average. And again, as we saw, the average often doesn't correspond to a value I can even ever measure. Right, in the previous 2 examples we did, we got expectation values of 0, despite the fact that any measurement will give us either plus or minus h bar over 2. The reason why we care is because of what we call the correspondence principle. We've seen this before with special relativity. The correspondence principle tells us that any model of physics that we have should always reproduce classical physics in the appropriate limit. In special relativity, that meant if speeds were very small compared to the speed of light, all of our relativistic physics should give us all of our Newtonian physics. The same thing is true for quantum mechanics. If I'm dealing with a system that is sufficiently macroscopic, for example, or high enough temperature, I should recover the physics that we know from our personal experience. For example, in classical mechanics, we know that the momentum of a system is equal to its mass times its velocity, which is its derivative of position with respect to time. Well, it turns out that in quantum mechanics, this equation is still satisfied, But what is momentum and what is position? It turns out that momentum and position are going to suffer from the same weird probabilistic ambiguity that we call superposition as spin does. And so if I can't even really establish what the momentum will be because it depends on, the whims of the universe at the time that I measure it, or the position of the particle likewise, then I don't know how to even equate these two things together. But it turns out, so this equation is actually not meaningful for quantum mechanical states because the states represent multiple possibilities. So the state of momentum represents multiple possibilities. The state of position represents multiple possibilities. And there's a correspondence between those possibilities. This equation doesn't capture all of that information. In quantum mechanics, however, what is satisfied is that the expectation value of momentum is equal to the mass times the rate of change of the expectation value of position with respect to time. And so all of our classical equations can be applied to quantum mechanics as long as we replace the variables with their expectation values of what we would get if we measure them. Alternatively, perhaps a better way of thinking about it is that these are the fundamental equations of nature, and it just so happens that in the classical limit, the expectation values are so well defined that it is almost completely unheard of for a measurement to be any value other than the value we expect it to be. In other words, classically, the measurements we make are the means. They are the arithmetic averages of all the possible quantum sort of superposition possibilities. But that the expectation value classically also happens to be the mode. And not just the mode, but basically the only possible value. So classically, the expectation value is reduced to the variables, but quantum mechanically, we have to actually draw that distinction. And so again, the reason why we care about expectation values is because those are the things that we can measure, and those are the things that we can relate to the properties that we usually associate with dynamics of systems. At this point, we're almost done talking about quantum spin. We're going to extend what we've learned about expectation values and spin operators just a little bit further next. And once we're done with that, we're going to leave spin behind, and we're going to talk about quantum states where we instead care about the position and the motion of particles rather than their angular momentum. And we're going to get more into the meat of wave functions and uncertainty principles and all of that. So hang with me. I know this is taking a little while and it's very abstract, but we are going to be able to apply what we've learned so far to analyze systems that I think are a little bit more fun.